Hey class, in today's lesson we're going to talk about polynomial models in the real world, which is found in section 5-8. Our objective is to fit data to linear, quadratic, cubic, or quartic models. Alright, so regression models. It says the behavior of the graphs of polynomial functions of different degrees can suggest what type of polynomial will best fit a particular data set. Type the following data set into your calculator and use the three different regressions, linreg, quadreg, and cubic reg, to determine which line is the best fit. Now, just as a reminder, to be able to type this information in, you would go to, on your calculator, stat, enter, because that's edit. You may need to clear out your list, so you go hover over L1 and L2 and press clear enter, and then you type in your information. So that's what I'm doing now. Alright, and then from there, if I want to do linreg, I would press stat, go over to calc, and go down to linreg. And so if I calculate that, the linear regression for this model, it actually gives you a function. But what I really want to take a look at is the R value, if you remember. So we need to turn on diagnostic on, and to get diagnostic on you press second catalog and go all the way down to diagnostic on. So I'm going to go back into here and do linreg, calculate, and what I notice is that my R for linreg, I'm going to put that in pink, is going to be 0.74, so it's about 74% accurate. Alright, I'm going to do the same thing with quadreg. I'm going to go over to stat, calc, go down to quadreg, calculate, and this one's a little better. This was 0.76 as far as accuracy. And lastly, I want to do cubic reg. So stat, calc, cubic reg, calculate, and I get 0.99. So actually cubic reg is our best fit here, and so that's great. Okay, so those are the different types of models, and so what that basically means is that these points better fit a cubic function than they do a linear function or a quadratic function. So the n+1 point principle, so it says for any set of n+1 points in the coordinate plane that pass the vertical line test, there's a unique polynomial degree at most n that fits the points perfectly. So let's take a look at what that means. So in example 1, it says what polynomial function has a graph that passes through the 4 points 0, -3, 1, -1, 2, 5, and -1, -7. So here's the deal. There are 4 points. So this is considered the n+1. So to be able to figure out which function would best fit, it would be n minus or n. Since this is n+1, it's 4, n would be 3. So the degree that matches this best is a cubic function. So since that's the case, we know a cubic function looks like ax cubed plus bx squared plus cx plus d. So what we're going to do is we're going to substitute these ordered pairs into as my x and my y into this function. Really, I should say y equals all that. Or better yet, I'm going to put y at the end, and you'll see why. So if I substitute in 0, -3, that's going to be a times 0 cubed plus b times 0 squared plus c times 0 plus d equals -3. We've done this before, by the way, guys. So our answer will be d equals -3. Okay, move on to the next one. That's a times 1 cubed plus b times 1 squared plus c times 1 plus d equals -1. And that expression would be a plus b plus c plus d equal to -1. Alright, keep going from there with the next point. A times 2 cubed plus b times 2 squared. Uh-oh, I skipped some stuff. A whole lot of stuff. Hold on. Got a little confused. Alright, so a times 0. No, I was right. 2 cubed. because we're talking about the third point. So 2 cubed plus b times 2 squared plus c times 2 plus d equals 5. And so that one will be 8a plus 4b plus 2c plus d equals 5. And then the last one with negative 1 and negative 7, that's a times negative 1 cubed plus b times negative 1 squared plus c times negative 1 plus d equals negative 7. And so that equation will be negative a plus b minus c plus d equals negative 7. So remember, we did all this when we were dealing with matrices. So if I put this into a matrix, that matrix would be 0, 0, 0, 1, negative 3, then 1, 1, 1, 1, negative 1, 8, 4, 2, 1, 5, and the last one would be negative 1, 1, negative 1, 1, negative 7. Okay, if we put that into our calculator, so remember we go to stat, let's see, you press second matrix. We need to go into the name, go over to edit. We're going to all pick A, and this is A. Remember, it's rows by column, so there are 4 rows and 5 columns, so this is a 4 by 5. Okay, if we type in all this information, then we press second matrix, math, RREF, which is B. Oops, actually we have to do that on the home screen, so sorry. Second matrix, math, RREF, and then go back in, second matrix, and we're going to pick name A. Your answer will look like 1, 0, 0, 0, 1, 0, 1, 0, 0, negative 1, 0, 0, 1, 0, 2, and then 0, 0, 0, 1, negative 3, which means that our function will be sorry, not A. Our function will be y equals x cubed, right? Because that's what my A is. This is my A. Okay, let me use a different color. This is my A, my B, my C, and my D for that expression here. So that's x cubed minus x squared plus 2x minus 3. Now, that was the very much longer and difficult way of figuring this out. But here's the deal. Since we know that there were 4 points, we said it was going to be a cubic function from the beginning, the easiest way to do this is just to go into your calculator, go to Stat and Edit, clear everything out, type in your ordered pairs. So for my x value, it's going to have 0, 1, 2, negative 1. Then for my y values, that'll be negative 3, negative 1, 5, and negative 7. Go to Stat, go over to Calc, go down to cubic reg. Since there are 4 points, we know that we should use cubic reg, so third power. Go down and calculate, and what you'll notice is that you get the exact same equation. So my suggestion, count your points, use one less, and then type it into your calculator. If you happen to have a lot more points in this, then you may want to use a matrix, but as long as we have points that satisfy for len reg, quad reg, cubic reg, and quart reg, I would use those. Okay, let's look at our try. So for our try, we're just going to start by putting this into our calculator. We're not going to do the long version. I just wanted to show you that so you have a backup plan in case you forget how to do this problem. But as our x values in L1, we're going to type in negative 2, 0, 2, and 3. Then for the y's, that's 1, 5, 9, and 36. Okay, we go Stat, Calc. This is 4 points, so we're going to use cubic reg. And that function will be, and it's not going to be so pretty at all, my goodness. Hold on, let me make sure I typed it in right. Yep, it's just not pretty. If I round to the nearest hundredth, that would be 1.67x cubed plus 1.3 times 10 to the negative 12 x squared minus 4.67x plus 5. Now, by the way, when we write a function and you have something like this, okay, that has times some power, that really means that that number is so close to 0 that it might as well be 0. So we're just going to rewrite it as y equals 1.67x cubed minus 4.67x plus 5. And we're done. All right, so now we're going to try and model this data. So it says the chart shows how much milk Wisconsin dairy farms produced in 1955, 1980, and 2005. What linear model best fits the data? Use the model to estimate milk production in 2020. So we technically already done this process before, but I just want to go over this process one more time because we're going to add something to it. So this, since it says linear model, we're going to use linreg. Okay, so in our x values of our calculator, we're going to type in, for our x values, we're going to use, and you want to be able to tell me, or you have to be able to tell me what your x values represent. So our x values will represent years since 1900. We could have easily said years since 1950, but we're going to use years since 1900. So years since 1900 would be 55 for the first one, 80 for the next one, and then 105 for the last one. Okay, our L2 would be 16.5, 22.4, and 22.9. Okay, it asks for a linear regression. So that function would be y equals 0.128x plus 10.36. Okay, now if we want to know what it is in 2020, our x value for 2020 would be 120 because 2020 is 120 years after 1900. So to find that, we would substitute in 120 for x. Let's see, 0.128 times 120 plus 10.36 will give us a milk production of 25.72 billions of pounds of milk. In 2020 is what I should have said, so in 2020. And we're done. All right, let's take a look at our try. Okay, so we'll have the exact same thing, except this time they're asking for an estimate in 1995. So if we remember, the equation was y equals 0.128x plus 10.36. 1995 would have an x value of 95, so we just substitute. So let's do that. 0.128 times 95 plus 10.36 would give us 22.52 billion gallons of milk produced, billion pounds of milk produced in 1995. All right, example 3. Okay, it says the graph shows, but clearly I didn't even put the graph on here, but all you need to know is that there's a graph that's shown in your book that shows the milk production of a model that was given in example 2 if I did it as a quadratic graph, okay? And so basically it's saying that the points from the milk production fit the data perfectly, just about exactly, okay? So it's saying, given that both models are good fits, which seems more likely to represent milk production over time? So this is really just a thoughtful type question. What do you think is the better fit? And so if you think about it, our data for a linear graph versus our data for a quadratic graph, right? If we're looking at only this section here, right? And you're thinking about milk production, which over time would be a better fit? Well, if you look at the linear value, what that would mean is that milk is just going to increase and increase and increase and increase and increase as time goes on. And I mean, there's not enough cows. I mean, there may be enough cows, but that doesn't sound like the better fit. So really, it's actually going to be the quadratic function, because as it increases, yes, it's going to start to kind of start to taper off. It won't be as high of a production over time. So, and the fact that, once again, we're dealing with 3 data points, and so the better fit would be a quadratic function. So that's what works best. So quadratic model is better. Okay. All right, so let's talk a little bit about reliable data. It says data generated by a law of physics or a geometric formula will have a mathematics model that fits the data and yields accurate predictions. For other data, such as sales records, you should only approximate the data close to the domain over which it was generated. So when we're talking about math formulas and stuff like that, it's accurate. Like, it's pretty much always going to be the exact same. But when you talk about things that kind of have to deal with outside factors, you want to try and only estimate information found within your data. So extrapolation versus interpolation, okay? So using a model to predict a y value outside the domain of a data set is called extrapolation and is considered less reliable as you move further away from the x values of the data. Estimating within the domain is interpolation and usually yields reliable estimates. So when we talk about information like the sales, basically things that deal with outside factors, okay, we want to look at data within, and so we care more about interpolated results versus extrapolated results. All right, so an example 4 says using interpolation and extrapolation. So the table shows the average annual consumption of cheese per person in the U.S. for selected years from 1910 to 2001. We're going to use cubic regression to model the data within a cubic function, then estimate the U.S. cheese consumption for 1980, 2000, and 2012. In which estimate do you have the most confidence, least confidence, and why? Okay, so this is a lot of information, so let's go ahead. Here's our table. So what we first want to do is type this information into our calculator. And again, you need to tell me what x represents. So in this case, we're going to say x values, ES, are years since 1900. Okay, so that way we are all looking at the same information and we're inputting the same information. So again, we're going to clear out this information. Okay, we're going to type in 10, 40, 70, 75, 95, and 101. Whoops. Okay, for L2, we're going to put 4, 5, 8, 10, 25, and 30. It asks for us to use cubic regression. So in that case, our equation will be, and I'm going to round everything to the nearest hundredth, so that's going to be y equals 9.24 times 10 to the negative fifth minus 0.00, well, that's going to be 0.01. Hold on. Let me start over. Okay, y equals 9.24 times 10 to the negative fifth x cubed minus 0.01 x squared plus 0.31 x plus 1.80. Remember when I said if we have something that is with scientific notation, it's practically zero. So we're kind of just going to ignore it. But in this case, yeah, we're going to ignore it. Okay, let me scratch that. We won't ignore it. I'll just go ahead and write it out fully, just because mainly I want to care about it because it is the highest power, it's the leading power or the leading term, so we want to be sure that we have that right. So this would be, remember, negative fifth means we move the decimal 5 places to the left. So this would be 0. Let's see, 5 places, 4 zeros, so 1, 2, 3, 4, 924 x cubed minus 0.01 x squared plus 0.31x plus 1.80. Again, if I had rounded everything to the nearest hundredth, that first term wouldn't be there, but I just want to throw that in the information anyway. All right, so we want to estimate for 1980. So at 1980, x would equal, let me use a different color. So in 1980, x would equal 80. So if I substitute that, then my y value, or my pounds of consumption, let's see what I get. I'm going to round this to the nearest tenth. I'll round to the nearest hundredth since I did everything else. So this would be 9.91 pounds consumed, okay? In 2000, x would equal 100, so we got to do the same thing. So let's see. Okay, that would give us 25.2 pounds. And then in 2012, x would equal 112, so then that means y, or our pounds consumed, would be wow. I think I made a mistake, so let me do that again. Okay, that was a mistake. Okay, so it's 40.90. Okay. Now, which ones am I most confident about? Which numbers am I least confident about? Well, we should be most confident about numbers that are interpolated, so numbers that are within the data set. So 1980, we should be able to feel pretty confident about. Even 2000, we can feel pretty confident about. But this 2012, we can't be as confident because it's not found within our data. So there's no way to truly tell if that is accurate because, I mean, if you think about it, in 2012, eating 40 pounds of cheese, that's kind of a lot. So anyway, we can only really feel confident about the first 2 pieces of data and not as confident with the last piece of data because it's not found within the data set. All right, guys, that is the end of this section. If you have any questions, please be sure to come in for tutoring so that I can help you out.